the integrals that we're going to do in this particular section are technically nothing that you should not have been able to do in Calc 1. I mean, that is, we're not going to introduce anything new. Although you're going to be a little amazed at just how much algebra may be involved. And if your algebra is weak, this is a great chance to work on it. So all I'm going to do is a bunch of integrals. Just, I think about 10 examples, something like that. Hopefully you can see the ideas that are used and apply them to your own homework. So without further ado, let me go ahead and start. These will be a mixture of definite and indefinite integrals. And the idea also is to sort of remind you of some things that you need to be aware of and some faux pas that you should avoid and things of that nature. Now, as you look at something like this, you could theoretically go, well, what if it usually comes down to a U-substitution, if you remember that. Trying to let something equal U. Letting U equal X, by the way, is never going to do anything. It's just going to change the letters of the problem. So you got to let it be equal to more than that. Some people might say, okay, I might let U be the square root of X. However, I say, why not let U equal the whole thing? Because when you take the derivative, the 1 will disappear, and you know when you pick a U, you're going to have to take a du at some point. So my feeling is this. I'm going to say let U equal 1 minus radical X, and then let's see what happens when I take the derivative. The 1, of course, goes away, but the other part, negative 1 over 2 radical X dx. And now we're in something of a pickle, because I don't have a 1 over 2 radical x dx anywhere in this problem. I mean, I've got the 1 minus x, radical x that is. Whatever you do, you want to mix u's and anything else. So let's just roll with this and see what happens. Now, so what do I do about this then? How do you fix something like that? Well, let me take this away for just a minute. And what I'm going to do, before I do anything else, is I'm going to add radical x to both sides, and I'm going to subtract 1. I'm going to square both sides, and then I'm going to take dx. Now, this is like a chain rule type of a problem. I don't want to actually expand it. I'm going to bring the 2 down, and the derivative of negative u is negative du. So now I can substitute everything I want. Let me take this integral down here. It's always a good idea to change your limits of integration before you do the rest of it, because a lot of people, being used to just regular indefinite integrals or just antiderivatives, they want to go and put everything back and then throw in the numbers. I don't think that's such a good idea. At least I think it's less efficient, and I think it's more error prone than anything else. So I'm going to change my limits of integration. Here's how you do it. X went from 4 to 9 when it was under X. Now we're doing U. This is some sort of a substitution. So what you do is, let's start with X equal to 4. If I take and replace X equal to 4, U would equal 1 minus the square root of 4, which is 1 minus 2, which is negative 1. Because I'm converting to U. Let's try it with the 9. Take the 9, plug it in for X. I'll have 1 minus the square root of 9 will be 1 minus 3, which is negative 2. Now I'll be able to replace 1 minus radical x in the denominator with a simple u, and the dx then will have to be replaced with all of this stuff. Now, there's a lot of stuff in there, but what I would do probably is you can either take this negative out front and use it to flip these, or you could take the negative and suck it into here, I suppose. I think I will do that part of it. I will pull the 2 out in front. So what I did is I took the negative and multiplied it through here, so that made it a u minus 1. The 2, of course, I pulled out front. Now, the easiest thing to do in these is to break this up into 2 fractions. So I could go u over u minus 1 over u du. Of course, u over u is equal to 1. And now we're talking about u, so when I take the antiderivative, it's going to be in terms of u. Of course, the antiderivative of 1 is u. The antiderivative of 1 over u is natural ln, absolute value of u. And that is going from -1 to -2. Now, the absolute values will be necessary because these are negative numbers. So let me go ahead and throw in my stuff. I'm going to have -2 minus ln, absolute value of -2, minus 2 times -1 minus ln, absolute value of -1. And let's evaluate. So I'm going to get 2 times -2 will be -4. Then I'm going to get minus 2 ln 2. I take the absolute value in that step. I'm going to get plus 2. But this part right here, the natural log of 1 is equal to 0, so it's not going to be there. And I can only do a little simplifying. I have -4 plus 2. That'll be -2 minus 2 ln 2. I will leave it to you to get the decimal versions of these answers. I'll leave them all, for the most part, in the exact format that I have here. All right, this time we're going to go from 0 to pi over 2. The square root of 1 plus cosine of 2x dx. Now, you might try a U-substitution, but if you let u equal anything cosine oriented, its derivative will involve negative signs, and there's none of those to be seen. So instead, use this identity. Cosine of 2x equals cosine squared of x, actually 2 cosine squared of x minus 1. Yeah, I think I'll go with that one. There's hundreds of them that I could use. So this will become the integral from 0, not hundreds, but there's several. So I get 1 plus 2 cosine squared of x minus 1. So I didn't even have to do a u du anything. The ones will cancel, and I will be left with 0 to pi over 2 square root of 2 cosine squared of x dx. I'll pull the 2 out, so it'll become a radical 2 in front. Now the square root of cosine squared is technically the absolute value of cosine of x dx. However, we're in the first quadrant and cosine is not negative there, so I can simply drop those absolute values. Of course, the antiderivative of cosine is sine. That's radical 2 times 1 minus radical 2 times 0. Sine of pi over 2 is 1. Sine of 0 is 0. So we end up with the simple answer, radical 2. All right, now this one, if you might think to try to factor it, it will not factor. Not in any good way that you're going to want to factor. So, and I'm not so sure that that would have done you any good anyways. However, one thing you could do is typically you might, as a test case, let u equal the denominator. But then when I take the derivative, I'm going to get 2x plus 4 dx. Now here's an issue. If I look to my in here anywhere, I do not see a 2x plus 4. This is, I can deal with this. I could put a 2 in front of there if I multiply out here by a half. But this 4, I don't know what to do about that. So this is not going to do me any good. But give me a second. Let me take this. I'm going to pull a 2 out of here. That still doesn't mean I'm going to use this. I recognize that if I had an x plus 2 up here, I could be working with something. So while this has provided me no help, watch what I'm going to do. This is a trick that you use all over the place. So I added and subtracted the same thing. I sort of forced an x plus 2 to appear there. So this becomes the integral from 0 to 2, x plus 2, Now, this hardly seems like anything easier, but right here, we could let u equal x squared plus 4x plus 8. And then du, as before, would be 2 times x plus 2 dx. So that integral, instead of going from 0 to 2, throw in 0, and you'll go from 8, and then throw in 2. Let me see, you get 4 plus 8 plus 8, 8 to 20. And instead of having du equals 2, what we can do is cancel that and put a 1/2 in front of the du. So I'll have a 1/2 here. This is all part of my du. And down at the bottom I have my u. That's an easy integral to do. Now for the second piece, give me a moment on it. I'm going to separate these. I'll bring the 2 out front. Now, this business in here, you may have remembered back in the day that you were required to do something called completing the square. The fact that you can't remember that doesn't mean that it wasn't shown to you. And if it was never shown to you, I'm sorry. I guess this is your first chance to see it. So what we do is we try to write this in something that is more convenient to integration. I'll show you what I'm talking about. We have x squared plus 4x plus 8. I could rewrite this as x squared plus 4x plus 4 plus 4. I broke the 8 up into 4 plus 4. And this equals x plus 2 squared plus 4. So let me put that down in there. Now, we are getting there. We are getting somewhere. You should recognize this as something that's close to what you want to do. I'll get to that in just a moment. I'm going to finish this one off here. So I get 1/2 the natural log of the absolute value of u, and that'll go from 8 to 20. I can drop my absolute value because the 8 and the 20s are positive numbers. Over here, I think what I'll do is I'll pick a different letter than the u that I use it for. I'll let w equal x plus 2, and then dw equals dx. Well, that's nice. So if I throw in 0 for x, I will get a 2 here. If I throw in 2 for x, I will get a 4 up here, and I'll have 1 over u squared. Now instead of 4, I'm going to do something sneaky with it. I'm going to write it as 2 squared. Do you see what happened? I didn't put that. Got to be careful. The reason why I'm writing it this way is because I happen to know that one of the integral tables that are in the back of your textbook deals with integrals of this type, and that's the whole idea. The whole idea is to monkey with these things enough to where you're going to get it into a format that you can recognize either by memory or in a table. So let me finish this piece again. I'll have 1/2 ln of 20 minus 1/2 ln of 8. And for this part here, well, actually I'm going to evaluate that now. Let's see, what I'm going to do is scan the tables and see if I can get any help in there. So I'm going to go, I have an online version of the book open, to Integral Tables. And let's see what we can find. I'll copy it and put it in the one that I think is right here. See this? Right here. I have a u squared, or I have a w squared plus 2 squared. This one right here is the most relevant formula. So let me grab that. You don't have to know what number it is in the book, but I guess I'll reference them in case you're using the same book I am. Right there. I'm not using x, but I'm using w. So the a here, a squared would be 2. So this equals 1 over 2. And I'll have arctangent x over 2. And that will be going from 2 to 4. Now, some of the things that I'm going to do next, it's not really required here. For example, you should know that I could combine the logarithms to get the natural log of 20 over 8. Okay, next, these 2's cancel, and I end up with negative arctangent of, if I plug a 4 into here, I'll get an arctangent of 2, and then I'll have, well, since there's a negative in front, I'll have minus a negative arctangent of 1. Well, that's equal to pi over 4. You can simplify this. If you divided this top and this bottom by 4, for instance, you'd have 5 halves. So you got 1/2 ln 5 halves. I don't know anything for arctangent of 2, so I'll just leave that. But I do know that that's pi over 4. And I won't bother doing anything else. This will be fine. Let's see, for anything that you want to get an answer in decimal format, any decimal that you write is an approximation. If you want to approximate that with the decimal, just use your calculator. Now this one will look very, very similar to the previous one, but it's not quite the same. In fact, the mechanics are quite a bit different, because in the denominator is something right here that squares. It's a perfect square in the denominator. I can rewrite the denominator as x squared plus 1 squared. Well, now I could use a nice u would be x squared plus 1, and then the du would equal 2x dx. And that's good because I needed an x dx. I didn't need a 2x dx, so what I can do is get rid of it here and divide by that instead. And I'll end up with 1/2. And so I'll have 1 over u squared du. The 1/2 du is accounted for. And that will equal 1/2. It's better to rewrite this, I think, as u to the negative 2 du. And this will equal 1/2 times u to the negative 1 over negative 1. Don't forget to put your plus c's in for those that are indefinite. And this ends up being negative 1 over 2u plus c, and then u was equal to x squared plus 1. So this equals negative 1 over 2 times x squared plus 1 plus c. Now, the variable of integration is irrelevant. Now I want you to see things from a perspective that is similar to the one before. What do you think? When you look at these, we didn't have a lot of things that dealt with the square roots of things in the denominator except for a very small collection of things. And I'll show you what those things are. It's stuff like this guy right here, number 13. Arc sine. A number squared minus x squared. Well, you saw here that our arctangent I was able to get through completing the square. So I'm going to do the same thing here. I'm going to complete the square. I'm going to rewrite the thing as negative theta squared minus 6 theta plus 27. Now, if you remember, the deal is you try to factor out whatever's in front first. So I've factored out the negative. Now, the next thing is to add in here half of this coefficient squared. So half of 6 is 3. So I'm going to take 6 divided by 2 squared. But to make up for the fact that you're doing it, subtract it off as well. And then what I'll get is negative. This part right here, x theta squared plus 6 theta plus 9 will be 0 plus theta plus 3 squared. And then that takes care of the first 3 pieces, but when I multiply through by the negative, I cancel out this negative, and I'll get plus 3 squared is 9, 9 plus 27. So that'll be 36. So my integral will turn into d theta over the square root of 36 minus theta plus 3 squared. So now I told you the one that I wanted. I'm going to go grab it because it really is starting to look like that now. Let me grab number 13. Alright, so if I want to make it look like this, I am going to have to do something with this because that doesn't have an x plus 3, that just has an x. So obviously the thing to do, I believe, is u equals x plus 3 and then du equals dx. That's really nice. So our integral then will become the d... So then du becomes d theta. That's beautiful. I can just change that to a du. Down here I can rewrite this as 36 minus u squared. And now I will appeal to the integral formula that says that this is arc sine x over a would be, in this case, u over the a. 36 is 6 squared. Remember, it's not 36, it's 6. It's the 6 that we want. Don't forget to see this was not a definite integral. And then I'm ready to replace the u back, which is the theta plus 3. All right, for the next one, we have an indefinite integral again. So I just have d theta. You're almost certain that you're going to deal with trigonometry when you see a theta. 1 plus sine of theta. Now this may look nearly terrifying when you first look at it, but there's a trick that you can use for this. Now obviously, if we had limits of integration, we'd be better informed, but we don't. So we just have to assume what we can. I'll have 1 over 1 plus sine of theta. What I'm saying is that I'm not going to really worry that this thing is not going to be defined whenever sine of theta is 1. If I was dealing with a definite integral, I would know the numbers that I'm working with and whatnot, and I would deal with it appropriately. The nice thing that happens here is the numerator doesn't do much. I have 1 minus sine of theta. but the denominator becomes 1 minus sine squared of theta, d theta. Now, from the most popular of all the trigonometric identities, you have got to have memorized cosine squared of theta plus sine squared of theta equals 1. So I'm going to throw those things in the denominator. Down here then, this becomes cosine squared of theta. And then don't forget the d theta. Now I'm going to do the trick that I did before. I'm going to break this up into two fractions. And I'll do one thing more. The first one I'll write is secant squared of theta. The reason why I do that is because you have a direct antiderivative of that, and that's tangent of theta. So I don't even have to do anything u-oriented. But for this part, I am going to use a u. And I guess what I should do is I shouldn't, well, I'll do it in the next step. I shouldn't be mixing u's and thetas in one step. So what I'm going to do here is say this. We're going to let u equal cosine of theta, so that du equals negative sine of theta d theta. And you notice that I have negative sine of theta accounted for there. So the first part of the integral will just become tangent of theta. And then for this part here, that negative is accounted for in the d theta with the sine theta and the d theta. So this will be a plus. And that integral will be cosine to the negative 2 power. No, u was cosine theta. So u to the negative 2 du. That equals tangent of theta plus u to the negative 1 over negative 1. Now put a plus c. And what was u again? U was cosine of theta. So that equals tangent of theta minus 1 over cosine of theta plus c. There's 100 different ways you can write your answer. I really don't care. You could write this as secant theta. You could probably combine fractions and some other stuff, but that's not here nor there. For this next one, I haven't had one of these yet. A e to the 2 radical x plus 1 all over radical x dx. And for this, what you might want to do is pick u to be radical x, but I think you could do a lot more than just that. I think try u equal the whole thing and see what happens. If it doesn't work out, I'll back off and maybe let u equal smaller things. But remember, e to the something, the integral of e to the something is just e to that something, assuming it's just something simple like an x or a u or something like that. So I'm going to try this. U equal 2 radical x plus 1, and then let me take the derivative. Du equals, the derivative of radical x is 1 over 2 radical x. So I'll have 2 over 2 radical x. And so that then becomes 1 over radical x dx. That's beautiful because I have that accounted for right there. That is my du. Beautiful. It's exactly what I needed to. So I have, then this works out beautifully. I have e to the u du, which we know is equal to just e to the u plus c. And I can simply put that stuff back in, and I'll have e to the 2 radical x plus 1, all in the exponent, of course, plus c. Another indefinite integral, and more e's. E to the 2x all over e to the 2x minus 4 e to the negative x dx. I'm not going to do anything u-oriented just yet, because that denominator does not look good. But what I'm going to do instead is this. That second part I'm going to write as 4 over e to the x. Now, as you might do with any other type of a problem, you might attempt to get a common denominator down here. And the common denominator that you'll want to get down there is going to be over e to the x. So the numerator, I'm not doing anything up here just yet. Let me make that clear. I'm solely working down here. I'm going to rewrite this as e to the 3x over e to the x. And then I'll go ahead and combine those fractions. So down here I'll get e to the 3x minus 4 all over e to the x. Now you might know that this is the time when you're going to flip this fraction in the bottom and rewrite this as e to the 2x. I'll think of it as e to the 2x over 1 times e to the x all over e to the 3x minus 4. And then I'll get e to the 3x in the numerator. So I haven't done anything yet except rewrite the problem. Used a little bit of simple algebra on it. But here, to me it seems evident, if I let u equal this piece, then my du will be this stuff. By the way, you should be thinking about this. Getting a du in the denominator is never desirable because, well, dx is not in the denominator, and dx will always be related to du. So, you do not want to ever get a du in the denominator. That's why I'm thinking of a u being this part, and the du would be up here with this stuff. So my thought, u equals e to the 3x minus 4. So then du equals 3e to the 3x dx. But I don't have a 3 in front of that thing. So I'm going to get rid of that and put a 1/3 du over there. So I'll have a 1/3 in the front. So I have everything accounted for. Here's my u, and the 1/3 du takes care of that. So I'll have 1 over u du. And then when you take the antiderivative, you get 1 over 3 ln the absolute value of u plus c. Well, what was u? That was e to the 3x minus 4. So I get 1/3 ln absolute value of e to the 3x minus 4. Now it's possible that quantity in the absolute values could be negative. You have to have the absolute values around those. Well, since I've done a couple of exponential ones, why don't we move over to logarithms. I'm a ln squared of x squared divided by x dx. And you can see that having a 1 over x kind of says, well, u should be ln of something, or maybe just ln of x if I could make it work. Letting u be equal to something is a trial and error method. You'll get better and more efficient at it the more of these problems you do. But the fact is, it's still trial and error. Let's see, I would think, I guess this is an x squared inside of here, so I might let u equal the natural log of x squared. Alright, and then du would equal 1 over x squared. That's the derivative of ln. But then you need to take the derivative, don't forget the chain rule, of x squared, which is 2x dx. Well, this is nice. Du equals 2 over x dx. This is close to what I wanted. I wanted 1 over x. I didn't want 2 over x. So, well, this is easy enough to deal with. I'll get rid of that one and put a 1 over 2 here. So my integral becomes 1/2. Now this is the natural logarithm of x squared squared. I had ln of x squared, but I didn't have a little 2 here, so this is going to be u squared du. And so that will equal, when you take the antiderivative of u squared, you'll get u cubed over 3. Combine it with that, will be u cubed over 6. And then what was u equal to? Ln of x squared. So now I can put, for my answer, I can put a little cube up here. Now let's put our u back. And we end up with ln cubed of x squared divided by 6 plus c. On this one, your book, or a book, had this, and the methods that I was going to use were very lengthy compared to what the answer that they had was. So I can be fooled myself sometimes as well. But then again, I have some tricks that perhaps they haven't seen either. So whatever, it doesn't matter. What I do tell you is this. Notice that sine is to the third and cosine is to the fifth. That's 2 more than the sine. So you might be led to line up cosine and sine to the same amount of power. So I might do something like this. Sine cubed of x over cosine cubed of x times 1 over cosine squared of x dx. Now, if you see, I guess if you see the trick happening, then maybe you're the kind of person that will see this type of way to do it and they'll just go with it and get the answer very quickly. I didn't happen to see it right off the bat. Right here, you should note that this is tangent cubed. So let me go ahead and do that. Tangent cubed of x. And this is not, you can rewrite this as secant squared. Now, you could let u equal tangent, because then du is secant squared x exactly. So at this point, you could let u equal tangent of x, and then du equals secant squared of x dx. So this integral reduces to u cubed du. That equals 1/4 u to the 4th plus c. Well, it's going to have trouble with 4's apparently. Let's make that more 4able. Make that more u-able. And then replace u with tangent. And we get 1/4 tangent to the 4th x plus c. And I only have one more example left. I guess I lied. I'm doing 11 examples. This one's going to knock you for a loop. Wait till you see this. This integral will be a definite, a definite integral. It will go from 2 to 4. You're going to have x squared plus 2 divided by x minus 1 dx. Now, I don't have a technique. If I break this up into things, and like you might want to break this into fractions, and you might go, well, if I take the derivative of x squared, I'll get 2x and I could work with something. But no, you're not going to be able to work with that, because then if you were to think of u being something like this, and then your du could reside down in the denominator, you're in big trouble. It's not going to work. Never put a du in the denominator. So I'm stuck here, but there's something that you can do. Do you recall? And you only do this when you're dealing with a rational function, a polynomial over a polynomial, where the numerator has a higher power or an equal or higher power than the denominator. And that's long division. Do you remember this? And the smart thing to do is to leave a spot for the x that's not there. And then you ask yourself, what do I need to multiply by x to give me an x squared? Well, you'd need an x. So you'd get an x squared but then you have to carry the multiplication through and get negative x. And that's why we put that thing there. Don't forget, you subtract this line, so 0 minus negative 1 will be a positive 1, and then you bring down the rest. And then I could add 1. I actually am being a little careless here, and I shouldn't. What you really should do is try to treat it as much like a normal long division problem as you can. What that means is when I multiplied it by x, I should have put it up here so that it matched up this place value, if you will. The place value is x to the 1 power. Now, then when I multiply by 1, so that only an x appears here, so I'll go plus 1, I'll have then x minus 1. When you subtract this line, you'll end up with a 3. Well, don't forget, that means that you rewrite the problem as this. 2 to 4, this stuff gets rewritten. This is the quotient. This is the remainder. And of course, that's the divisor. So this becomes x plus 1, the quotient, plus the remainder over the divisor. One thing you should take a quick look at is that since x minus 1 is in the denominator, x cannot equal 1. They have avoided that with this interval. Well, now it's really simple. For this piece here, I don't think I need to tell you of a du substitution. Let me go ahead and write the next line and see if you can hang with me. The antiderivative of x, of course, is 1/2 x squared. The antiderivative of x of 1 is x. And then here, this will be 3. Now think about this for just a minute. If you let u equal x minus 1, du would be dx, so it already matches that. So you'd have 3 over u. The antiderivative would be 3 times the natural log of the absolute value of u. But then I'd put my x minus 1 back. So if you followed all that, try it on your own. I don't want to mark up the page with so many different variables, so I'm trying to avoid that as much as I can. So all of this is going from 2 to 4. So let me go ahead and throw the 4 in. I'll have 1/2 times 4 squared plus 4 plus 3 ln 4 minus 1. I won't need those absolute values, by the way, but I'll keep them there just so you can follow along. Minus, then I have 1/2 times 2 squared plus 2 plus 3 ln 2 minus 1 in absolute value. This equals, well, 4 squared is 16 times 1/2, so that'll be 8 plus 4 plus 3 ln of 3 minus 4 times 1/2 is 2, and then I have another 2 there. Ln of 1 is 0, so I'll have, well, this 4 can cancel with those, and it looks like I'll have 8 plus 3 ln of 3